It's fine. Good afternoon, everyone. I would like to thank the organizer for providing this opportunity. I'm PhD student at the University of Memphis. Today, I'm presenting one of my research work focusing on the study the adhesion characteristics of Mars-1 regolith on polymeric substrate. I believe this community will learn about the challenges of the regolith accumulation. So I'm not taking too much time to explain this. The extensive research being conducted to overcome these challenges, but still some further investigation and analysis is necessary as this challenge, like the challenge of the dust mitigation, is not fully overcome. As the contribution to this field, we are conducting research works on the adhesion characteristics of Mars-1 regolith on the space grade materials. Next slide, please. The materials we have chosen in this research is aerogel, PDMS, and ceramics. They have been using for the space exploration, such as aerogel, which is using in the thermal and acoustic insulation, hypervelocity particle capture, and so on. This is the image. The left bottom one is the image proposed SAMA collection sample model containing silica aerogel. And the other materials we chose is the siloxane-based polymer called the polydimethyl siloxane. They use in the calibration target, radiation shielding, etc. And the third class of materials is the ceramics. They have been using for the thermal barrier coating, sensing application, and the thermal protection. Next slide, please. These materials are chosen based on their specific suitable property for the space applications, such as aerogel is known for the low density and high thermal insulation materials. Initially, they were not considered as the mechanically robust, but the advancement in techniques made able to create the mechanically robust aerogel by cross-linking. One of the cross-link aerogel we use in this study is the polyurea cross-link silica aerogel. I will call PCSA throughout my presentation. The other materials is the polydimethyl siloxane. They can withstand high temperature swings from cryogenic to 300 degrees centigrade. They are easy to synthesize and chemically inert. Third class of materials which have not been widely explored, but they have the attractive property for space application is flexible ceramics, specifically flexible yttria stabilized zirconia, which is we know that the ceramics can withstand temperature up to like high temperature up to 3000, and the advancement in technique make them possible to make in the thin sheet, and these thin sheet are flexible. They are chemically inert. So we are interested to see that how the regolith interaction and the adhesion occurs in this substrate. Next slide, please. So as these materials have been using for the space application, we are interested to see that how regolith adhesion occurs and interaction by changing their surface potential and based on the particle size. Next slide, please. So to conduct the research, we employed these methods. We prepare a synthesis sample. We change their surface property by neutralizing or charging them. We measure the surface potential immediately after neutralizing or charging, and we attach that sample in the Z-axis movable stage. In the inverted setup, I'll explain in the next slide about the inverted setup. And we lower to make the regolith interaction. The charge of surface we lower to make the regolith interaction, and we did the different analysis. Next slide, please. So as shown in the left side images, we charge the sample by corona discharge method, and then we put it in the inverted setup. We choose the inverted setup to avoid the gravity assisted adhesion, and then we lower the charge sample to make the interaction. This third image shows the regolith interacting or lifting up towards the charge sample. We systematically increase the surface potential by changing corona voltage from 0 to 10 up to 30 kilovolt, and we do extensive research on the different particle size from the 14 like the up to 300 micron. And next slide, please. Then after charging, we are interested that how these surfaces like the affect by corona discharge method. So we measure the surface potential over the time, and we observe that the relatively PDMS, which is polydimethyl siloxane, gains the relatively high potential compared to other substrate, and YSC ceramics, interestingly, does not gain too much surface potential. And the other thing we observe is the post PCSA, which is aerogel, has the gradual decay of the potential. Next slide, please. Then after we expose the charged surface in the Regolith surface, can you play the video, please? Okay, this is the interaction of the regolith on the charged surface. As we lower the charged surface, the regolith is attracting towards the surface. And to quantify the force acting on the regolith particles, we modeled this system as the parallel plate model, and the charged top surface considered as the one plate, and the regolith layer is considered as the other layer. Due to electrostatic induction, regolith particles gain charge and then they lift up toward the charged surface. This video was played in the 4x speed. Next slide, please. So we calculate net force acting on the regolith particle using the standard, like the standard accepted theory. And interestingly, we observed that the electrostatic force on the regolith particle is not enough to overcome gravitational and van der Waals force on the regolith particles. We can see in the graph that the red bar is the electrostatic force, which is too minimum to overcome both gravitational and van der Waals force. Next slide, please. So based on the experimental evidence, we hypothesize that there should be particle-particle repulsive force, which is responsible for the lift of the particles to the height of first interaction, and which observed from these images, as we increase the particle diameter, the interparticle spacing is increasing. So it happens in the both substrate aerogel and then the PDMS. So the left-hand side image is the particle size of less than 45 micron, and then the middle one is for the 180 to 90 to 180 and 180 to 300. So next slide, please. We quantify the particle spacing, and we found that the interparticle distance increases with the increase in particle diameter. So what we believe is the one particle diameter increases, the charge acquired by this particle increases, and that causes the more repulsion between these particles. Next slide, please. So the other part in this research is we quantify the mass accumulation on the substrate, and we observe that the mass accumulation increases with the applied voltage and particle size, both PDMS and PCSA. But in the YSC ceramics, the regolith is lift up, but they did not adhere on the ceramic surface, so it was hard to quantify the mass accumulation. Next slide, please. The other parameter we quantify is height of first interaction. We observe that the height of first interaction increases with the applied charging voltage, and both PCSA and PDMS, but it is quite similar for the ceramic substrate. Next slide, please. The other quantity that we were interested is surface coverage. We found that the surface coverage for the both PCSA and PDMS increases with the applied voltage, but decreasing with the particle size in the both substrate. We believe that this is due to the particle repulsion force, and which increases with the increase in applied potential. So as we hypothesized earlier, the further confirmation, like the one experimental evidence is shown by the surface coverage. When you increase the particle size, the coverage decreases. Next slide,
30
please.
seconds.
Next slide, please. In summary and conclusion, we found that the both PCSA and PDMS acquire surface potential. I'll not go through all things. I already explained the most of the things. Next slide, please. So I'd like to thank my supervisor, Dr. Firozi Sabri, for her guidance and support throughout the research. Next slide, please. Thank you.